Okay, so now we are ready to write the equation to describe the rotational dynamics for rigid bodies. So we have Newton's second law. And Newton's second law says F equals ma. So there's going to be an equivalent equation for rotational dynamics, and it says that torque is equal to I alpha. So alpha is the angular acceleration and I is the moment of inertia. So alpha plays a role of the acceleration in this equation and I plays a role of the moment of inertia. So let's see how we get to that. So let's start with this particle here, right? So this particle is moving with some velocity and it has some angular acceleration and it has an acceleration at, right? So at, the acceleration of the particle is alpha r. It also has a centripetal acceleration, but we're not going to worry about that for now. So that's the linear acceleration, right? So what this is called the tangential acceleration. So now we know that the tangential acceleration is alpha times r, so we can write alpha is equal to the tangential acceleration divided by r, right? So we can plug this here and we get this equation, right? So alpha is F divided by mr. So now if I multiply by r top and bottom, I get alpha is equal to Fr divided by m r squared. Or this is the torque on top, and then you get mr squared. So this quantity mr squared is what we're going to call the moment of inertia, and it plays the role of the mass in Newton's second law of motion. So then remember, torque is r times F, so therefore alpha is torque divided by mr squared. So if we have a rigid body with many forces being applied, then we can write the same equation for the rigid body, right? So we can think of the body as made up of little masses, right? So this body is rotating about this point, and then each mass has a torque, right? And then we can write using that equation that we have there, alpha is equal to torque divided by mr squared. We write that, we rearrange that and write it for each one of the masses. Now we notice that alpha is going to be the same for everybody, right? So then we simplified alpha, right? And then we get alpha, and we call this whole thing here, this is going to be the moment of inertia for this rigid body. So that's the definition of moment of inertia. And so the moment of inertia is a quantity that opposes rotation in a way. It tells you how difficult it's going to be to rotate something. It depends on the axis of rotation. The moment of inertia, if I want to rotate about this point, is different than if I want to rotate about this axis. And then we are now ready to write Newton's second law for rotation, which is the angular acceleration is equal to the net torque divided by the moment of inertia. So that's equivalent to A is equal to F net divided by M. M plays the same role as I in this equation here. So let's think about the moment of inertia a little more. So imagine that we have this distribution of masses here, this merry-go-round here, right? If the children are at the edges, then you're going to have to apply a larger force to get this to rotate than if the children are close to the axis of rotation. Remember that you have this equation here, right? This r is just this distance here. So if you want to reduce the moment of inertia to make this easier to rotate, what you need to do is move the masses closer to the axis. So how the mass is distributed affects the moment of inertia and how it is distributed around the axis of rotation. So we can now write a synthesis for our Newton's second law for rotation. So remember that we have F net is equal to ma, that's Newton's second law, right? And for rotation, then we would have net torque is equal to I alpha. So you have the same quantities here: net force, net torque, mass, moment of inertia, and then alpha and acceleration. So then the equation reduces to Newton's second law.
Is there something else I can help with?
Sorry, my series just not helping. So moments of inertia of common shapes. So in this class, you're not going to be calculating any moment of inertia. There is a table in the book that you can consult to get the moments of inertia that you need. Here is a moment of inertia of a bar if you're rotating about this axis. Here is a moment of inertia of a bar if you're rotating about an axis that is at the edge. Here is a moment of inertia of a square. You can have the moment of inertia of a cylinder, a ring, a square about an axis that is along the edge, and finally a sphere. Those are the most common moments of inertia, and a shallow sphere, right, a shell, so that you're going to be using. Let's do a little example to close this video. So we want to calculate the time that it takes for this thing to fall. So this that is 5.9 meter tall. The mass is 79 kilograms and is tipped by 25 degrees about the vertical and is starting to rotate. So what is the time that it takes to fall? That's what we want to. So we can draw a picture here, right? So we have this angle here is 25 degrees. So this is the center of gravity here, right? And that's where the gravitational force is applied. So the torque would be this component times this distance. So the torque is W sine theta multiplied by L over 2. That is your torque. So, and then the gravitational force is mg, so the torque comes to be mg times mg sine theta times L over 2. That's your torque. So that's the only force being applied. So we are not going to, there is a force being applied here, a normal force, but that force doesn't produce any torque because it's applied at the axis of rotation. We're considering rotations about this point. So now we can apply Newton's second law. We have the torque here. And then we're going to use the moment of inertia of a bar about this axis here. That is 1/3 of ml squared. So we simplify the whole thing and we get this equation. We put in the numbers and that gives me the angular acceleration, which is 1.1 radians per second squared. So now we applied our rotational kinematic equation. The final, that's theta f, the final angle is equal to theta I, which is where we can set that to 0, right? Plus omega I, which is 0 times delta t, plus 1/2 alpha delta t squared, right? So this is 0. This is 0, which is this quantity here, and all I'm left is with this one here, and I can solve for delta t and find that that is 0.4 seconds.